This presentation focuses on motion, specifically kinematics. So when we study motion, we will talk about describing the motion of an object, and that's really kinematics. So we'll talk about things like speed, velocity, and acceleration. And then later on, we'll talk about why objects move. How do we change the motion of an object? And that's the focus of that is dynamics, but we won't be talking about that in this presentation. So the first thing that we'd like to do is describe the motion of an object, and how do we do that? What do we need to know in order to describe the motion of an object? And so one of the things that we might be interested in is where is the object located at a particular instant in time? And that's described as the object's position. We also might want to know how far an object moves. So does it move a large distance? Does it move a small distance? And over what time interval does it move through that distance? But not only do we want to talk about distances, we also want to talk about something called displacement, which is different than distance, but they are kind of related to one another. So we'll talk a little bit about that. We'd like to know how fast an object is moving from one place to another, which would be described as the speed or the velocity. Again, these are similar to one another, but not exactly the same. And finally, we'd like to know, does how fast the object is moving change over time? And that's described as acceleration. So we have these terms, position, distance, displacement, speed, velocity, and acceleration, that are going to describe the motion of an object, and we're going to define all those quantities as we go through these presentations. So the very first thing when we're talking about the position of an object and the distance that's covered is that we need to have some type of a coordinate system. So if I want to describe the position of an object at a particular instant in time, I have to be able to say, well, it's at this particular location, and the only way to do that is to have a coordinate system. So we're going to start with one-dimensional motion, and so we'll just look at the horizontal direction, and we'll use a traditional coordinate system, which would be the x direction along the horizontal axis. And so in this particular picture, we have a representation of an object, and the dots on here represent the position of the object at equal time intervals, specifically 1 second time intervals. So at time t equal to 0 seconds, the object is at the origin of the coordinate system. After 1 second, it's at 0.5 meters. At 2 seconds, it's at 1 meter, 3 seconds, 1.5 meters, and so on. So the axis along the horizontal is my position axis. It's labeled x, and the units that we have here are units of length in meters. So anytime we have these representations with these dots, it's representing where an object is, the position of an object, over equal time intervals. So in this particular example, what can we say about the motion of this particular object? Well, the first thing I realize is that the dots are equally spaced, and of course these are equal time intervals. So I see that the object covers the same distance each second that goes by, right? So in the first 1 second interval, the object covers 0.5 meters. Between 1 second and 2 seconds, it covers another 0.5 meters, and so on. So the equally spaced dots represent the object covering the same distance every second that goes by. So we could certainly look at this particular motion, which is a very easy motion, and sort of try to understand what's going on with that motion. So the first thing we could describe is, what is the object's position at particular time intervals? So at 2 seconds, what is the position of the particle? And at 5 seconds, what is the position of the particle? So if I look at 2 seconds here, I realize that on my coordinate axis that the object is at 1 meter. And then if I go over to 5 seconds, I realize that the object is at 2.5 meters. So at any given position, or at any given time, I can figure out what is the exact position of this object at that time interval. I can also ask, what distance does the object travel between these two times? So between 2 seconds and 5 seconds, what distance was actually covered? So it's the distance between these two points, the 1 meter mark and the 2.5 meter mark. So the distance traveled between those two times is 1.5 meters. So there's a lot of information that I can get from having this description of the motion of an object that's represented by these dots that show where the object is every second that goes by. So that brings us to the first expression that we want to define here, which is average speed. And so average speed is the measure of the distance covered in a particular time interval. So it's basically the rate at which we cover distance. So this is an average, so we have to be careful. It's not telling us something specific about the motion at a particular instant in time, it's telling us an average. So for example, suppose I took a trip and I go from my house and I decide to go to the beach, and I cover quite a lot of distance. So maybe it's 100 miles to the beach, and it takes me 2 hours to get there, right? So my average speed would be my distance covered, which is 100 miles in 2 hours, right? So 50 miles per hour, 100 100 miles over 2 hours. But that's just an average speed. So that doesn't mean that I'm always traveling 50 miles per hour. It means that maybe sometimes I had to stop at a light and I had to wait, but other times I was on the highway and I was traveling, 65 miles per hour or something like that. So this just gives us an example of the fact that it's an average, right? So it's telling us something over a time interval, but if that time interval is big, it doesn't tell us a lot about the motion of an object. But it is an important thing that we think about, because it tells us something about, if we look at small time intervals, we get closer to understanding what's going on at that particular instant in time. So when we're talking about speed, the units that we use in physics, the standard units that we use for length are meters, and the units that we use for time are seconds. So this is highlighted in green because that is the standard unit in physics that we would use. But of course, we know that there are other units that we could use. For example, I just said miles per hour, and I used miles per hour because that's an example of something that we would look at our car and we would measure how many miles we go, and we would probably measure our time in hours. So certainly there are other types of units. Anything that's length over time, like centimeters per second, feet per second, or even kilometers per hour, would be appropriate units for speed, but keep in mind that the standard unit that we will always go to would be meters per second. When we're talking about the average speed of an object, the direction doesn't matter, and it's always a positive quantity. So it doesn't matter my trip from my house to the beach. It didn't matter that I had to go around turns, or that I had to go north and then I had to go west or south or whatever. The direction doesn't matter when we're talking about the average speed. So let's look back at our example and see if we can calculate the average speed of this particular object that's traveling from our previous picture over different time intervals. So the first thing is, what is the average speed of the object below for this picture in the time interval between 2 seconds and 5 seconds? So we know the average speed is the distance covered over the time. And we found from the previous example that we looked at that between 2 seconds and 5 seconds, the distance covered is 1.5 meters. So I go to 2 seconds, 5 seconds, right? That distance covered is the difference between 2.5 and 1. And the time interval is just the time interval between 2 seconds and 5 seconds is 3 seconds. So my distance covered is 1.5 meters. My time interval is 3 seconds. And so my average speed between 2 seconds and 5 seconds is 0.5 meters per second. I could also ask the question, what is the average speed of the object over the entire time interval shown? So over the entire time interval shown, the distance covered is 4 meters and the time interval is 8 seconds, right? So 0 to 4, 0 seconds to 8 seconds. And so if I went through and I calculated the average speed again, the distance covered is 4 meters, the time is 8 seconds, so again I get 0.5 meters per second. So I'm not always going to get the same exact value for the average speed over different time intervals, so this is a very special example. In this particular example, the motion of the object seems to be uniform, and when we say uniform, it means it's moving at a constant speed. So the object covers the same distance every second, the dots are equally spaced, and that represents the object always traveling basically at the same average speed over any time interval that you look at. When the speed is constant, then you can make predictions about the motion. So we could ask, knowing that the speed of that particular object is constant, can we predict the distance that the object will travel in a time interval of 20 seconds. So we know that the average speed is the distance covered over the time. And so we can multiply both sides of this equation by time. And if we multiply both sides of the equation by time, it cancels out the time on the right side, multiplies the time on the left, and we get that the distance covered is just the average speed multiplied by the time. Now this will only work for a good prediction if the speed is constant, and it is in our case. So we know that our average speed is constant at 0.5 meters per second, and our time interval is 20 seconds. So I can put in my average speed, multiply by my time, and my distance covered is going to be 10 meters. Of course, the other way we could have done this is to look at those dots and just keep putting those dots in, and we know that every second that goes by, we just have to add another half of a meter, and by the time we got to 20 seconds, we would have gotten to a distance of 10 meters. So this is a very special case when the average speed is actually a constant value over the entire motion. One of the things that we're going to spend quite a lot of time on is looking at how we would graph the motion. So we've represented the dots that hold the position of the object every second, and we can also make a graph of that. So this is a graph of the position of that object versus time, and essentially almost over 20 seconds. I guess I missed out the last part of that graph. But if we look at what this graph looks like, right, at 1 second, so again, here's the position axis is on the vertical and the time axis is on the horizontal. So after 1 second, I've gone a half of a meter. After 2 seconds, I've gone 1 meter. 3 seconds, 1.5 meters. And by the time I get to 5 seconds, 2.5 meters, and so on, right? So if I got to the 20-second mark and the graph ended, but it should go all the way up here, it would be 10 meters. Or if we go to 8 seconds from that previous example, right, it was at 4 meters. So this is a representation of what the graph would look like if we were to plot that particular motion of the position versus time. And one of the first things that we should look at, or we should realize, is that this is a straight line graph because the speed is constant, and it has a constant slope. So remember, the slope of a graph is just the rise over the run. And no matter what point I look at here, if I were to take the rise, so let's say the rise at 8 seconds is 4 meters, over the run here is 8 seconds, I get 0.5, right? So 4 over 8 is 0.5. If I go over to 4 seconds, I have 2 meters, so the rise is 2 over the run, which is 4 seconds. So the slope of this graph is constant and it's a positive value. We could ask, what would the graph look like if the object was actually traveling faster? So if it was traveling faster, that would mean that it would cover more distance every second that goes by. So after 1 second, instead of being at 0.5 meters, it would actually be higher because it would be covering more distance. So for an object that's traveling faster, that it would still be a straight line, but it would have a steeper slope. And for an object that's traveling slower, it would have a slope that is not as steep, right? So these representations for these lines of position versus time tell us a lot about what the motion of the object is in terms of how fast it's going. So slope of the position versus time graph is always going to tell us something about the speed of the object. All right, so here is just an animation that's going to allow us to see the motion of an object with different speeds. And so where the dots are on here, right, these are just the same representations we drew before, and it just shows the object every second that goes by. And then a graph of the position versus time for each one of these is made above, right? So for the first one, It covers less distance every second that goes by, right? So it's a flatter line. And then the second one covers more distance every second that goes by, so it's steeper. And then finally, the last one covers much more distance every second that goes by, and it's very steep. So this is just a little animation that sort of shows us what the position versus time graphs would look like for these different motions, where the dots represent where that object is every second that goes by. So we could also ask the question, what would the graph look like if the object was traveling in the negative direction? So instead of traveling to the right, maybe this object is actually traveling to the left. So here's the object, right, moving at a constant speed, but it's traveling to the left instead of traveling to the right. And so if the origin of my coordinate system is someplace over here, the object is starting far away from the origin of the coordinate system. So in my example, it's starting at like around 12 or 14 meters from the origin of the coordinate system, and it's heading towards the origin of the coordinate system, right? So it's heading, so maybe it started off at 12, and then it was at 10, and then it was at 8, and then 6, and so on. And so it's heading towards, over time, it's heading towards the origin of the coordinate system. So my position versus time graph still looks very similar. Here's my picture. So, so this would be the reverse, right? So at 0 seconds, right here, the object is at 4 meters. After 1 second, it is at 3.5 meters. After 2 seconds, it's at 3 meters, and so on. So it starts off away from the origin of the coordinate system at time t equal to 0, and then as time goes on, it heads towards the origin of the coordinate system, right? So it's heading back down towards the 0 mark over time. So this object is still covering the same distance every second. It's still covering 0.5 meters each second that goes by. However, it's traveling in a different direction, and if we make a position versus time graph for that, it's represented by still a straight line, but it has a negative slope. So not only does the slope of the position versus time graph tell us something about how fast the object is moving, it's also telling us something about the direction that it's moving, right? So this has a negative slope, and the object is actually traveling in towards the negative, or in the negative direction. It's traveling towards the origin instead of away from the origin.